Okay, today we're going to be talking about 4.1, where we talk about exponential functions. And an exponential function is any function where the variable, the independent variable, is typically referred to as x, or sometimes we use t for time, but that variable needs to be in the exponent. So in all of these examples, this variable here has to be considered to be in the exponent. So the script on the software didn't let me go too high with that exponent, but imagine that it's in the exponent position. A couple of things you need to know. The base, b, needs to be positive and constant, so a number like 4 or 1/2. They cannot be negative though. You can put a negative out in front, like y equals -2 times b to the x, and b could be like, maybe we'll make that just 6. So b is 6 here. The -2 is not part of the exponential. It's an afterthought or a multiplier that comes in after the fact. Again, we call this term, this number, the base. So in one case it's 2, in another case it's 5, then it's 4. And then we have our exponent. It could be x, or it could be something like x plus 2. We'll talk about what that x plus 2 means. A lot of what we're going to do, we're going to focus on graphing, and you can graph these things with a calculator. Pretty straightforward, just need to evaluate different data points. Now we can also do it by hand, and that's what I'm going to do here. If I want to do it by hand, I need to set up a t-chart. And once you know what these look like, it only takes a few points. But I'm going to run the points -3, -2, -1, 0, 1, 2, and 3, just to prove exactly how this looks. Now 2 to the -3rd, we have to remember, means 1 over 2 to the +3rd. Okay, that's what that negative does, it reciprocates. And so 2 to the 3rd is actually 8, so this would be 1/8. Then 2 to the -2, we're going to flip it, become 2 to the 2nd. Okay, that becomes 1 over 4. Then if I put a -1, that makes it 1 over 2 to the 1st. That would be 1/2. And then anything to the 0 by definition is 1. Sorry, I was saying 0 and writing 1. I ended up writing 0, but it's a 1. And then 2 to the 1st, of course, is 2. 2 to the 2nd, of course, is 4. And 2 to the 3rd is 8. If I were to try and plot these points, some of them get really tough, like this 1/8 of the way up, or even 1/4 is kind of hard to work with. 1/2 is a little bit more reasonable. 1, we said at 1 it would be 2, at 2 it would be 4, at 3 it would be 8. So we can see this curve is starting to really climb pretty quickly. Now this is going to stay right above the x-axis, and we're going to roll this up this way. Whoops, like that. So remember, this is going to stay above the x-axis. It's just going to cut really, really close to 0. So a couple of things to keep in mind. Okay, never reaches 0, what we're going to call 0. Now if I do some modification of the equation, this number could be 1, it could be -4, but there will be a line that it never crosses, never reaches. And then over here, this is something that might seem a little misleading. It gets very vertical, but it always moves right. Meaning that it doesn't get truly vertical. It never goes straight up and fail to go to the right. It will always go a little bit to the right. And so that's important to remember. Now that allows us to understand why the domain is all real numbers, because this graph does go forever left and it does go to the right forever. There are no breaks in the domain. However, like we said, there's a bottom or a flattening area where the graph sort of dies off. We call that our cutoff value, or our horizontal asymptote. And our range on most equations will be greater than or equal to 0, or sorry, greater than 0, because we get close to that 0. However, there will be values and times where we drop that number. Remember, 0 doesn't have to be the boundary. We can change that. And so we'll have to be specific as we look at that. And if it's just a basic function, then the point 0, 1 will be a valid point for all of them. So if b is greater than 1, meaning we have something like y equals 4 to the x, the bigger the exponent, the more this is going to spike upward. And so our graph is going to look very similar to this. Okay? The bigger we let x get, the more it becomes a huge thing. And if we use negatives, it flips it upside down and makes it really small. If, however, b is between 0 and 1, for instance, y equals 1/2 to the x, then this is going to do the exact opposite. Okay? it's going to start out really big because a negative, remember, flips this upside down, makes it 2. And so when it's negative, it's going to go up really fast, but then as it comes towards the positives, it'll flatten out. 1/2 to the 10th means 1 over 2 to the 10th, and that's going to be a huge number, and 1 divided by that huge number is going to be really small. So this is going to get really tiny really fast as we go to the right. So let's look at a couple of transformations we could look at. One of the things you want to keep track of is the fact that these are written essentially in the format b to the x minus h plus k. Now h, k is our transformation. Now keep in mind, we always do the opposite of what's grouped with x, so any subtraction here would actually turn into be a positive, any pluses here would actually be a negative, and then k would be just the way it is. If I look at this example problem, this is all in the exponent, so keep that in mind, it's all the exponent. That tells me that I'm doing x minus 1, so in this case h would equal 1. K, there is no plus something or minus something at the end of the equation, so k would be 0, meaning that I'm going to go right 1 space and up and down 0. Okay? I'm not going to move up and down, but I will move to the right 1 space. So if I look at this example problem, I could take this point right here and come 1 to the right. I could take this point right here and come 1 to the right. I could take this point right here and come 1 to the right. Here to about here. Here to here. There to about there. And we can see that we get the same sort of equation, graph shape, but it's been shifted always 1 space to the right. Sorry, this is a little bit hard to draw with this mouse combo I have right here, but you can imagine how this is going to go following the same pattern, but it has been shifted 1 space to the right. Over here it gets really hard to see that it's been shifted to the right, but it has been. It's just that it's so close to the x-axis that it's hard to see. But this is a graph that's been shifted right 1 space. And you knew it was going to be right or left because it was with the x in the exponent. Now this plus 1 is not in the exponent, which makes k equal 1, which means everything goes up 1 space. And so I can literally take every point and come up a space. Take a point, come up a space. 2 is there, I can come up to about there, here to whoops, I'm moving up too much, sorry, I'm counting by 2's. That's my fault. Let's redo that. That's going to come to right here. There's where 1 is on the axis. Then this will come up to about here. This will come up to halfway, so ignore those for me. This one will come up to about here. This point here will come up to about here. Am I doing that right? Yeah. Let's do this point here. Come up to about there. And we're kind of running out of room. Okay, and so we've moved up 1, moved up 1, moved up 1, moved up 1. We moved up 1 there, moved up 1 there, and we keep going up. And so we get the same graph. In this case, what's interesting is the bottoming out of the graph is here at 1. So you know the range would actually be y is greater than 1 instead of being greater than 0 because of that transformation or shift. All right, now we have the natural base. The natural base is a number that was developed by a man named Euler. That's why we use the little e to represent Euler. And it says that we have a value of 2.718, and then it kind of goes on from there. And so we have the special button on our calculator. We'll use it. An example question on page 379 talks about the population of the world, and it was 3.6 e to the, I don't remember. Hold on just 1 second. Let me grab that. Sorry, 3.6 e to the 0.02x. And this talks about the growth of the world population. And there's a theory that 10 billion people, this was a theory developed in 1969, that 10 billion people was all that the Earth could sustain as a planet before we start to lose our comforts, if you will. Things become a lot more stressful. And so the question is, how dangerous is the world's population getting in terms of that? Now, obviously, things have changed since 1969. Our ability to grow food efficiently is different. Our ability the technology we use to purify water and do things like that has definitely changed in pretty dramatic ways. However, if I wanted to stay with this, let's just explore the population of the Earth today. Now, we were looking at this just the other day, and it says that we're at 7.4 billion is the estimated population of the Earth. And if we used today, 2017, then we would have 0.02 times 48 years since 1969. And if we put that in our calculator, let's grab a calculator so everybody can see what we're looking at. We would start with 3.6, and then second, my e with an exponent's here. There's also an e here. Either one of those will work, but I'm going to do this one. E to the 0.02 times 48 equals 9.4. So the population this year was predicted to be 9.4 billion. Now, we know that we have not reached 9.4 billion. Things have changed. Now, was some of it because we're concerned about these overpopulating the Earth? Maybe. But there were also other things in technology and family life that have changed, and that's given us a change there. The next thing that would probably be pretty important to you is understanding how interest is accrued. Now, this interest works for you when you're putting money in a bank, but it also works against you when you're talking about interest on a credit card or some other type of loan. There's two different types of interest that we're going to compound. One is compounding it n times per year, so that could be 10 times or 12 times a year if it's monthly, 52 times a year if it's weekly. Just depends on those things. And then we have compounding continuously. Compounding continuously is going to use e as a value. In the equations, a always is the amount in the account. P is the principal. I like to also think about it as what was put in the account. Interest rate, of course, needs to be changed from like 8% to 0.08, and n is the number of times we compound. In this equation, we use n twice. Down here, when it's compounded continuously, we don't use an n. The e takes place of all of that. And then t is the time in years. So let's take a quick look at an example problem. It says you want to invest $8,000 for 6 years. You have a choice between two accounts. The first pays 7% per year, compounded monthly, and the second pays 6.85% per year, compounded continuously. Which is a better investment? So if we look at the first option, A equals P times 1 plus R over N to the NT, or we can use A equals PE to the RT. Now you cannot tell which one's better unless you actually do the calculations. They're not a quick, easy way to tell. And so we're going to take our amount, that's what we're looking for, is 8,000 times 1 plus, my rate in the compounded monthly account is 0.07 over 12 times a year, because it's monthly, raised to the 12 times t, which is 7 years, or 6 years? 6 years. We'll figure out what that is here in a second. Over here, we'd have our 8,000 times my e raised to the r is 0.0685 times my time is 6. So let's go ahead and evaluate the two of these. Use my calculator real quickly. And over here on the compounded monthly, I would just be really careful how I put it in. So I'm actually going to do 1 plus 0.07 divided by 12. I'm going to hit enter. I'm going to raise that to the 12 times 6. Make sure all of that's in the exponent. And then I'm going to times that by 8,000. And I get 12,160.84. So $12,160.84. That's a good return on my investment. $4,000 in 6 years. Definitely worth my time to invest that money. Over here we do it again, but this time with the PERT equation, or the compounded continuously. And this one's a little easier to type in. 8,000 e to the 0.0685 times 6. And I'm going to get 12,066.60. $12,066.60. So the better investment in this case is my compounded monthly account. But I know that if I went beyond 6 years, if I went to the 7th or 8th year, that this account here will start to really catch up on me. Yeah, it has a lower interest rate, but over time it's going to be able to catch up and grow at a really effective rate. But there you go. Good luck, and we'll see you in class.